Hi everyone, welcome to my talk. Today I'll talk about chunking, and this is work with my graduate students Michael Allen and Isabella DeStefano. So many visual working memory studies focus on relatively simple situations with objects that we don't know much about, but the real world is made up of objects to which we have existing knowledge. And so for example, we know strawberries are red and that eggs are yellow inside white. So the question we'll ask today is, how do these previously learned regularities that allow us to sort of chunk the world impact our working memory for these objects? And while most work about chunking is really focused on verbal information, FBI, some work has looked at this in the case of visual objects, including some work from me and my colleagues in 2009, where we showed people color pairs, so little colors inside of each other, and then probed them on some of them. And when the colors were completely randomly assigned, people stay relatively constant in their performance across the entire experiment. But in another group of participants, we made there be chunks, so that yellow would frequently occur inside red and blue frequently inside black for these participants, but not all the time. And these participants improved significantly across the course of the study, showing they were learning something and it was improving their ability to hold these items in working memory. And we showed this wasn't just guessing using these 20% of trials where they were different. Why does this happen? Well, what's the nature of this kind of chunking? Imagine you see a new egg, a single egg, and you have to hold it in working memory. We know you're going to be better because somewhere in your long-term memory, you have the knowledge that an egg is sort of yellow inside white. But what is it that you actually hold in working memory? One view that you might call the content-free view says that the reason you're so much better at holding these items in mind when you have chunks is that all you're storing is pointers. You're just storing a sort of content-free pointer. You say, I know this was an egg in this location. And on this view, of course, you've lost all the instance-specific information. All you would know about the colors is sort of what your prototype egg looks like. By contrast, another view, a view I'll propose today, is that in fact the egg pointer does help you, but it helps you by serving as sort of a retrieval queue for retrieving the specific colors that of this particular instance. That is, that the entire set of information is stored actively in working memory. This is a sort of distributed, more hierarchical view of how memory works. How can we test these two? How can we tell these two apart? We decided to use first a study where we looked at memory for the colors of objects. So you'd see some objects in different colors, and then you get probed on one location in a 4 alternative forced choice task where you had to know both the object identity and the color that object was in. And just like in that original 2009 study, we had sort of high probability pairings, so that like the backpack would often be red, but not always, which again allowed us to ask about guessing. And we made one important tweak that helps us tell apart those two views. We had the items vary trial to trial randomly in luminance. So while backpacks were frequently red, their luminance was completely random, sort of like in the real life where lighting might vary. Okay, so what happened? First of all, when all people had to remember was the color, they improved across the study. That is, they learned that backpacks were red, they formed chunks, and they went from remembering them as red and backpacks separately to red backpacks. The question is sort of what happens when we ask them to know more than they could have in long-term memory. And the content-free view actually suggests that you should get worse across the experiment here. As you switch from just encoding red and backpacks separately to encoding a red backpack chunk, you should rely solely on your long-term memory for what color the red backpack was or the yellow stapler. And so you should actually get worse at knowing the trial-specific information. And by contrast, our view where you're storing a sort of pointer and the structure associated with it, using it as a retrieval queue, suggests that you should actually improve in the detailed condition as well, because you're building these pointers that are going to help you store more information altogether. What did we find? Well, we found that the detailed performance went up. So in fact, instead of trading off with regular performance, as you'd expect in the content-free view, both improved as people learned this long-term memory information. Okay, you might wonder, maybe people haven't learned these objects well enough. We wondered that too. So we ran another study where we used existing chunks, words, versus scrambled words. And we asked people to remember, again, both the chunk relevant part, the letters, knowing this was up should help you remember the letters, but also the font, which was totally arbitrary for each letter in the display. We found, as you would expect, that having them appear in words, chunked together, helped you know the identity of each letter. So chunking helped. But we also found that actually you were better at knowing the font when they had appeared in a word, as though you were storing not just a pointer to a word, but also the structure within that word. Okay, so overall, we're proposing a new view of chunking. Rather than this content-free view, we think you have enhanced knowledge of the trial-specific perceptual details of items that can be chunked, rather than losing such details, a hierarchical view. And chunks as effectively cues that facilitate the encoding and retention of perceptual details as part of this sort of distributed hierarchical memory, not just pointers. Thank you.